Okay, so let's get started. Good. So we are going to continue our discussion on problems in distributed systems related to coordination. We will basically talk about termination detection, which was a problem I introduced last time before we ended the class. I'll talk about leader election and mutual exclusion. But before we start, I wanted to make some announcements. The first one, I already sent an email about this. There is an exam coming up on Monday. Okay, so it's an evening exam. It's going to be in the ILC building S140 is the room number. Okay, so make sure you make a note of that. It is going to cover everything from the very beginning through what we did until this Monday. Okay, what we are going to do today is not going to be on the test. It will be on the final, not on the midterm. Okay, so you still have to pay attention. Now, it's a closed book, closed notes exam. Okay, it's going to be 90 minutes in length, very similar to in terms of length to the sample exam I put up. Homework 3 actually has a sample exam attached to it. Okay, that was exam from 2 years ago. So it's a real exam. So that should give you a sense of what to expect and so on. Okay, and solutions to that exam are also posted on Moodle just so that you have a reference. Okay, so closed book, closed notes exam, 90 minutes. The best strategy to study for the test is to make sure you understand the lecture slides. Okay, don't start with the book and start reading 300 pages. That's not a good strategy because the material has been reorganized, some of the material has not been covered and so on. Start with the lecture notes, okay, rather the lecture slides. Make sure you understand everything that's in there. I'm not going to ask about things that are not covered in the lecture. Okay, so you are not expected to know things that we have not discussed in class. So I'm going to focus entirely on the class. So you should start with the lecture slides, use that as your study guide. Look at every topic that's on the slide, then go to the book or any other material if you need additional explanation. The lecture videos are all there. You can go back, review it. The lecture notes, there are scribes taking notes for every lecture, so they are also there. Okay, so you should have plenty of material to study the topics. If there are questions, come ask. We have office hours every day this week. Okay, in every week, but clearly this week as well. Okay, so that's about the midterm. Any questions about the midterm? So because there is going to be a class or rather an exam on Monday evening, I am going to cancel the class on Monday. Okay, there will be no lecture on Monday because it doesn't make sense to have lecture and then few hours later have an exam. So you don't have to worry about coming to the class on Monday. The other announcement is there was at the very beginning I had scheduled a couple of makeup classes. One of them was going to be this Friday. You will see that on the schedule. There's one next Friday. Okay. This Friday I decided because there's exam coming up and there's a homework due and all of that, I'll just not have it because that way you'll have a little extra time. Okay, next Friday, as it turns out, I have to go somewhere for a meeting, so I cannot actually be here during class time. So I'm going to cancel that class as well. I will reschedule them because we are a little behind schedule, so I still need to have a couple of makeup classes just to keep up. Otherwise, we'll have to drop some topics at the end. So I would rather not do that. So I'll reschedule them and let you know. You don't have to come this Friday or next Friday. Okay. Those are all the announcements with regards to the classes. As I had also said in an email, the lab 1 grades should be given out soon as tomorrow, I believe. Okay. We will also make a list of do or don'ts or common mistakes that we've observed across many groups and make a document and share it with you so you can learn from what to avoid in lab 2 to further improve your grade and so on. Okay. By and large, I think things have gone well. There are some groups that have not read the instructions carefully or misinterpreted what was being asked and so on. But for those of you who put in the work, I think things seem to be going fine. But you will see your lab grade coming out soon and there will be personal feedback on what your lab showed in terms of what we were expecting, and then we'll give you this document as well. Okay. Lab 2 is already out. Okay, as some of you have, we gave it out during spring break. The deadline is going to come up right after the exam, which does not leave a lot of time. Okay. So, I am going to see if I can give a couple extra days. We do not have too much time to extend it by a week, because lab 3 is supposed to come out right when lab 2 comes in. But I can see if there is a little bit of wiggle room and extend it by maybe to Monday or something like that. Okay. So, you will have a little extra time. Okay. But do not wait until the last minute. The single biggest mistake people made last time was they started on Friday, and the thing was due on Sunday, and ran out of time to do a few things that were asked. That seems to be by and large the biggest mistake we have seen. Okay, many groups seem to have made that mistake. So, start early and just look through everything, and you should be fine. Okay. Any questions? All right. So, let us get the lecture going. So, this is a quick recap from last time. I already covered this slide. We were looking at an algorithm to capture the global state of a distributed system. What this means is the global state is defined as the local state of each process and the set of all the messages that are in transit. And the reason we want to capture the global state and store it on disk is some processes of this distributed application fail, you can restart those processes from the state you saved on disk, which is also called a checkpoint in many cases. Okay. So, you want to restore this global state and then have applications continue from the point of the failure. Okay. So, we are going to assume that that you do not have perfectly synchronized clocks in your distributed application. Okay. So, and every process is independent, they can communicate, but they are independent. There is no global clock. So, we want to still capture a distributed snapshot, and I talked about what could be a consistent snapshot and what is not consistent. And the quick recap is, if you actually have a snapshot in which the sending of the message, okay, is actually happening after the snapshot, but the receipt of the message has actually happened before the snapshot, that is inconsistent, because if you restart the application, that message will be sent another time. It has already been received and processed, and you will get two messages. You will get a duplicate message, which will cause an error. Okay. So, it is fine for the send to be before and the receive to be after, but you cannot have messages being received before the sent from a snapshot perspective. Okay. So, you want to avoid the problem. Okay. Now, with that recap, I am going to discuss the distributed snapshot algorithm. Okay. This algorithm assumes that the processes, there are n processes, okay, they communicate using TCP. Okay. The reason we need TCP are for two reasons. Okay. It does not actually have to be TCP, but the property we want are that there is no packet losses. Okay. If messages are lost, then the algorithm does not work. Okay. So, it is a reliable channel, and it is an in order delivery, which means that if you send two packets out, they are actually going to be received in the same order. You will not receive them out of order. Okay. So, essentially we need reliability of the channel, and we need in order on every socket, and TCP gives us those properties, okay, out of the box. So, we will just assume TCP channels. Okay, but any network protocol that gives those two properties should be fine with respect to this algorithm. Okay. And the technique, so there are n processes. Okay. Any process can kick off the distributed snapshot algorithm, okay, saying it is time to take a snapshot. Okay. What it will do is it will first checkpoint its local state, which means it will take all of its memory contents and write it out to disk. Okay. That is what checkpointing local state means. Okay. You take everything that you have the process has in memory and write it out to disk. That's, so, you will do that. Okay. And then what you are going to do is you will send a marker message, okay, on every outgoing connection, which means on every open socket you are going to send out a marker message. A marker message simply tells other processes that a new snapshot has started, it is time to take a snapshot. Okay. So, any process can initiate the technique, okay, the algorithm, and to initiate your checkpoint your local state, you send a marker message on outgoing channels. Okay. Now, when any other process receives a marker message for the first time, it will realize that there is a has been started, it will do the same thing. If it is the first marker, which means the first time it has been told that there is a snapshot, you are going to essentially checkpoint your local state and send out marker messages on your outgoing channel. Okay. But you will do one more thing, which is now that the snapshot has begun, you are going to start recording all the messages that are coming in on incoming sockets, okay, until you receive a marker on the incoming socket as well. Because you have to capture messages in transit, once you taken your local snapshot, you will start recording all your incoming channels, okay, and start keeping a copy of every packet on your disk. I am going to show you in just a moment. Okay. And then once you receive a marker on your incoming channel, you are going to stop saving messages. Okay. So, process will finish when it receives a marker on each of its incoming channels. So, here is an example of what can happen. Okay. So, here is process A. Connection. They are shown by these two arrows. Okay. So, we will assume that A starts snapshot. Okay. Each process or each machine has a local disk, of course. Okay. So, A is going to write out its contents. Okay. So, it is going to write this out from A to disk, and then it is going to send a marker message on its outgoing channels. There are two outgoing socket connections, so you send a marker message. Okay. That's just a special message that tells other processes that it's time to take a snapshot. Okay. And then at the same time, you have to start recording incoming packets, which means there are two incoming sockets for A. Okay. So, if there are messages coming on these incoming sockets, you have to essentially write them out to disk as well until you get a marker on each of these. Okay. So, now this message M might reach B and C. Let us say it reaches B first. Okay. So, this message is arrived here. B will say time to take a snapshot. It will write state out to disk. Okay. And it will send out marker message on its outgoing channels. Okay. So, here is an outgoing channel. So, you write a marker here, you write a marker message here. Okay. And then it will start recording its incoming channels, okay, which is basically here. And so, you are going to start recording that until a marker message comes. Okay. Same thing is going to happen to C. There are, as you can see, that there are two marker messages, one sent by A, one sent by B. In this case, one of them is going to reach it first. That's the first marker. So, let us say the one from A reaches it first. It is going to write out its state, and then it's going to send a marker message here, and it's going to send a marker message here. Okay. And then you will see that because once you receive a marker, you send out a marker on each outgoing channel, and your outgoing channel is someone else's incoming channel. Okay. You are going to be receiving all the processes that are recording on your incoming channel will eventually get a marker message, because the other end will take a checkpoint and then send you a marker. So, in this case, these two messages will get recorded, a marker will come in, these two messages will get recorded, marker will come saying stop recording, and the same thing elsewhere. Okay. Once you finish this, what you will be left with is a copy of each of these processes memory contents on their local disk, plus a copy of all the socket messages that have come on the incoming channel, which are essentially the messages in transit. Okay. That is the algorithm. Any questions on this? Yes. Okay. Question. Good question. The question is, will they stop executing, write their state out? Because you want to write the state in a consistent fashion. As soon as you get your marker message, you can take a small pause, write out its memory contents, and then continue. Because what you do not want is, as you are writing, if the memory changes, then that does not give you any consistent state. Okay. So, you can take a brief pause, you can take a snapshot of your memory contents, and then continue from that point on. Don't stop for the whole thing to while the whole process is executing, only for you to write out its memory contents. Okay. Any other question? Okay. So, there are many things you need to understand. The first thing is, will this technique actually terminate? Okay. Will it actually end, or will there be markers floating around that will just keep this process going? Okay. What you should realize is, of course, the termination is actually fairly straightforward. Okay. You can reason about termination from a two process example. Even that. A and B are a distributed system. Okay. Let us say either of them can start distributed snapshot. Okay. They will then, let us say B starts it, they will write its contents out to disk and send a marker message on its outgoing channel, which is here, and it will start recording packets that are coming on its incoming channel. Okay, and B will stop only when the marker comes on its incoming channel, because that's what we said. You record your memory state and you keep recording all packets that are coming on your incoming sockets until you receive a marker, and B will only stop when that marker comes. The question is it guaranteed excuse me, is it guaranteed that it will receive a marker message? Okay, to understand that, you will have to see what A is going to do. Okay, so what will A do? Okay, A is executing. At some point, B's marker message will arrive at A because B sent it out. Okay, what will A do? Okay, it will basically do the same thing. It will write out its memory contents. Okay, and then it's going to send a marker on its outgoing channel. Okay, there's only one, so it will send that out. That message will at some point, okay, reach B, at which point B will stop recording. Okay, is that clear? Because that's the reason we assume that no packets can get lost, because if the marker message gets lost, termination is not guaranteed, because you will never stop recording if there's no marker message. Because we assume that messages don't get lost, you're delivered in order and so on. Okay, simple properties, but they allow us to get what we want. Yes, question?
But then if there are like many more than just A and B, won't there be like many other markers also?
Okay, that's a good question. The question is, if there are more processes than A and B, will there not be many more markers? And as a 3-node example, you can have arbitrary number of nodes. The thing you want to realize is that there will be a marker message coming on every incoming channel. Okay, why is that? Okay, because when you take a checkpoint, you send a marker message out. Okay, and in the worst case, that marker message goes to the other process and it sends you a marker message back, because its outgoing channel is your incoming channel. So anytime you send something, when it reaches C, there is going to be one coming back. The better case is C got a marker message. Either case, there's a marker message that you are going to get, which will cause you. So all you need to look at is a pairwise connection between any two processes. If you send a marker message to that process, it is guaranteed that a marker message has to come back, because at the worst case, that's the one that will trigger the checkpoint and it will cause the other one to send one to on its outgoing channel. Okay, so if you analyze it that way, every process will actually have that property, and you will essentially be guaranteed termination. Okay.
And then when you resume, won't you have like just so many marker messages that have come in from like many different processes?
When you resume, don't you have, you need a marker message on every open socket connection. Socket connections are pairwise. There's no requirement that, let's say there is another process D. Okay, there's no requirement that every process has a socket connection to every other process. You just look at whatever the application is doing in terms of regular communication. For all open sockets, you are going to send a marker message. Okay? In this case, I just showed a fully connected graph. That's not necessary. Okay, you can have any arbitrary sockets between any subset of the processes. The point is, whenever you get a marker, you will send it on existing socket connection. It doesn't mean you send a marker to every other process. That's not what is being said. Okay?
And if there's a process which is not
If there's a process that is not communicating with anyone else, what happens? In that case, the process is not part of the distributed system, and there is nothing it needs to do. Okay? In a distributed system, we are assuming that there are a set of processes that are communicating with one another. Those are the ones that participate in a snapshot. If you have a process that doesn't communicate with any other process, that's a centralized application. It can take any snapshot it wants. There is no communication involved there. Okay? Yes, question?
It says there that each marker is has an initiator ID, right?
Yes, so I'm going to, yeah, what is the question?
And you said once you receive a marker, that is after you send, you stop. So is there a requirement that you receive the marker that you sent out is when you stop, or any incoming marker?
Okay, question is, should you stop when you get a marker based on the marker you sent or any other marker. So the point is that you will get a marker only once and only once. Okay, because the point we are trying to emphasize here is you checkpoint only when you receive the first marker and send outgoing markers. Okay, so in the case of C, the example I was giving, A sent it a marker, B has sent it a marker because they took the checkpoint first. So C is going to receive 2 markers. The first one will cause it to take a checkpoint. The second marker will simply tell it that it's time to stop recording, because that's now an incoming marker. It does not tell it to take another checkpoint. Okay, so it doesn't matter why the marker came. Okay, all you need to do is if the first one you take a checkpoint, all subsequent incoming markers are simply telling you to stop recording at that point. Okay. Now the other thing is there could be multiple independent snapshots in progress. Okay, A and C can decide independently to initiate a checkpoint. Okay, and those could be executing concurrently, but we separate them out. Should assume that that's a 2 different instantiation of the snapshot algorithm. So we can essentially assign a snapshot ID to the marker messages. So you can say snapshot 1 versus snapshot 2, so you don't confuse the markers. Okay? So that's what is said here. Multiple snapshots may be in progress. Each is separate by tagging it with either the snapshot ID or initiator's ID. So you just treat them as 2 snapshots that just happened independently. You don't confuse the markers up. Okay, is that clear? Okay, so now if you execute this algorithm, you are going to actually get the property we wanted, which is you can realize here that we are not taking the snapshots at the same time, because clocks are anyway not synchronized. You take snapshots at different times, but it will guarantee us that you get a consistent cut, which is the property we were describing last time, which says even though the snapshots are taken at different times on different processes, if you actually restart the processes from these checkpointed states and replay all of the messages that no messages will be lost, no messages will be delivered twice, and actually be consistent. Captures local state of a process and it captures all the messages that are in transit. Okay, any questions on this? Okay, so we will continue. So here's a picture that's taken from the book. It's the same picture that's shown here. So here is a process. There's a marker that comes in. Okay, and that process essentially has 1 incoming channel. It has in this case 2 outgoing channels. Typically sockets are bidirectional, but let's leave that aside. So you will see that in this case Q wrote out its memory content to disk. It sent markers on outgoing channels, and it's going to start recording all of its incoming channels, and you'll see that messages A, B, C, D got stored until a marker came in. Okay, that's just pictorially showing the same thing I described here. Okay, so we will now use the distributed snapshot technique to solve another problem, which is called termination detection. Okay. Termination detection is the problem of detecting when a distributed computation has actually finished. Okay. And what does that mean? What do you mean by finished? By finished, we would mean that every process in the system has finished all of its computation, and there are no outstanding messages anywhere in the system that can trigger new computation. Okay. So every process has finished, it's processed all the incoming messages and no outgoing message to send, then all the processes are going to sit there doing nothing because no new messages are going to come. They have finished all the local processing they had to do. Okay. At that point, you can actually shut down all the processes because you know that they cannot make any more progress. They have finished all of their computation. Okay. So the question is, how can a process figure out whether it is done and it should terminate itself? Okay. So you can say, let's say the user watches all these processes. It's a user's job to kill the application when it's done. That's one approach. Okay. What if we want the application itself to figure out when it's done and have all the processes exit themselves? How can it do that? Okay. So now each process has to figure out whether every other process is done. Okay. So let us say a process is sitting there as part of an application, it has not gotten any work for a while, it is just sitting there idle. Okay. It needs to figure out, is everybody else done, can we all exit. Okay. So, that technique to figure that out is called termination, and it is a very simple process. What you are going to do is simply ask. Okay. So, the termination detection is essentially going to say, let us query all processes. If every process tells us they are done, then everybody is done. If any process says, no, I am still computing, then you basically say, let us not exit, let us wait for that process to complete its computation, maybe it will trigger new messages that do computation on other processes and so on. Okay. So, here we are going to have a termination detection algorithm that has two kinds of marker, a done marker and a continue marker. Okay. So, done marker is a query saying, are you done? Continue says we are not done. Okay. So, in this case, any process can start a snapshot, and as part of the snapshot you can send a done or a continue to all of its or send a query rather to all of its outgoing channels, okay, and then wait for responses. Each of those nodes is actually also going to query its neighbors and so on and get responses back. Okay. So, the response you are going to send to your predecessor is going to be done if all of your outgoing neighbors tell you that they are done as well. Okay. But if any one of your neighbors tell you they are not done, you send a continue message. Okay. So, there is one of two. Continue says let us not end, done says we are done. Okay. So, you send this query, you wait for all of the responses. So, if all of the queue successors send a done, okay, and queue has not received any messages, you will basically send a done, otherwise you are going to send. Okay. Yes, question. Okay. So, good question. How do you define what's a predecessor and what's a successor? Okay. So, we will have an arbitrary topology. Okay. So, I'm going to draw a second picture here. Okay. So, let's say A. Okay. So, here are some processes A, B, C, D, E, and the edges indicate who has socket connections with each other. Okay, so, arbitrary communication happening. Okay, there is no structure here yet. Okay, but let us say B decides it wants to start the termination detection algorithm. Okay, so B is done or not. Okay, so E has to reply. In this case, A will basically ask its neighbors first. So, because it knows B is asking it, so it's going to ask C saying, what's your status? Are you done or not? C in that case is going to ask D, are you done or not? Okay, well, B could have actually sent that message that way as well. So, you will basically get a natural tree that forms because you are sending these queries out, and then responses will trickle backwards. Okay, depending on who asked you first, you send the response to that node first. That node will aggregate all the responses, and if everyone says they are done, it will tell, and if that node is also done, it tells its parent that I am done. Okay. So, based on how the query propagates through the network, a topology will be formed. It is a connected graph. So, we will assume that the structure is actually formed based on how queries propagate. Okay. Is that clear? Any other questions here? Okay. Okay, so it's a simple extension of a distributed snapshot algorithm to also ask if processes are done or not done. Okay, so we are going to shift gears and talk about leader election. Okay, this is actually part of your lab, so you should pay attention because you are going to use one of these techniques in your lab. Okay, so what is the leader election problem? Okay, the leader election essentially says in a distributed system of n processes, we want to choose a coordinator node. Okay. Typically, your application developer decide what the coordinator node should be. Okay. But now, if that node actually fails for any reason, okay, coordinator by its own, the name suggests that it is coordinating something. Okay. If that node fails, and that coordination of whatever task was being looked at is no longer feasible. Okay. So, ideally what you want is that the responsibility of the coordinator node should be dynamically assigned to some node in the system, and if that node either fails or decided no longer wants to be the coordinator, a new node should be chosen. dynamically, and the processes that are actually part of the system themselves pick the coordinator node rather than an external system administrator or the developer. Okay. And so that is the problem of leader election. So you want to elect a leader, the leader becomes the coordinator. Okay, what it's coordinating is not our problem in this case. Okay, that's what whoever is implemented the leader election will decide. Okay, so for example, if you want to do clock synchronization, you have a time server. Okay, the time server is a coordinator that actually broadcasts the time to all other nodes, so they get synchronized. It runs the clock synchronization algorithm. Okay, the time server can be actually chosen as a leader election problem. Okay, rather than saying you are the time server, okay, you can pick that leader dynamically. Okay. So this allows us to ensure fault tolerance because the coordinator, okay, in most of this distributed application is an important process, and without that coordinator application will fail. So you want the ability for some other node to take over that task should a coordinator fail. Okay, and then which node should take over the task is decided by the leader election problem. Okay. So essentially how is this going to work? The processes are going to run an election, okay, to vote and figure out who the leader should be. Okay. The leader election algorithm should have some properties. It should actually elect one leader, not more than one. That's going to cause a problem because you want a unique coordinator. Okay. It should actually result in an election, meaning that somebody should be elected and you don't want two nodes to be elected. If you have those two properties, then I think we are good. Okay, so I'm going to start with some very simple algorithms. Okay. The first one is called the bully algorithm. Okay. It's actually a very straightforward algorithm. Every process is going to have a process ID, a numeric ID. Okay. We will number processes from 1 through n. Okay. And our goal in this case is we can pick whatever metric we want to pick the leader. In this case, the metric is the process that is alive with the highest process ID is going to actually get elected as the leader. Okay. Typically, you don't want process ID. I want the node that has the least load because the coordinator will mean it's or the node that has the best bandwidth connection or some other metric like that. But it doesn't matter what the metric is. In this case, we are going to just say highest ID process wins. Okay. So the leader election basically is going to have to figure out what's the highest ID process that's still alive and then declare that to be the new leader. Okay. And the bully algorithm is going to do that. It's a recursive algorithm, as you will see. Okay. And it is best shown with a picture. So there are three messages. Okay. There's an election message. Okay. There's an OK message and there is an I1 message, and I'm going to show using a picture how this works. Okay. So any process can initiate an election. If you feel the coordinator is not responding to you, you can assume the current coordinator is crashed, failed. Okay. So it's a time to elect a new leader, and then you can start the leader election algorithm. And the way it's going to work is as follows. So this is a picture that's just showing you an example. Okay. In this case, processes are numbered 0 through 7. There are 8 processes. Okay. Process number 7 was the coordinator. That was the highest ID process, and it has failed. Okay. So no longer responding. So 4 detects that there is no coordinator. It says let's run a new election. So the way now 4 has to figure out if there's any higher ID process higher than itself that's still up. Okay. So the way it's going to do the leader election is going to send messages to all other processes that have ID greater than itself. And we'll assume that you know the IP addresses of those processes and so on. So in this case, 4 has sent an election message to 5, 6, and 7. Okay. So if you get an election message from a lower ID process, okay, you simply send an OK message back. Okay. That OK message tells that process to the, in this case, node 4, 2 things, that there is at least one process that's higher ID than itself that's still alive, okay, and that it does not need to be the leader because there's a higher ID process. And then if more than one process says okay, you say you figure it out. Okay. So now this process is going to, so 4 is going to drop out saying that I don't need to be the leader. Okay. So 5 and 6 are going to figure this out. So 5 and 6 will actually run elections themselves. 5 will start an election, okay, recurs. And so 5 has sent a message to 6 and 7. Okay. And it turns out that 6 will also start an election. In this case, it's going to send a message to 7. Okay. Now, as part of 5 selection, 6 is going to send it OK. Yeah, because if you receive an election message from a lower ID node, you send an OK message. That's the rule. Okay, so this figure shows there are 2 elections in progress, one that 5 has started and the other one that 6 has started. So 6 is going to send an OK to 5, which will cause 5 to drop out. Okay. Now 6 is still querying 7. In this case, 7 has failed. Okay, so 7 is not going to respond. So 6 will realize that it is actually the highest ID process, because the only one process that has ID higher than it is down. Okay. So 6 in this case is going to, so 6 caused 5 to drop out, then 6 will declare itself to be the coordinator by sending an I1 message. So it is going to broadcast everyone saying I'm the new coordinator. Okay. Is that clear? Very simple recursive algorithm. Okay, the algorithm assumes that while the election is in progress, that a failure is not occurred. Okay, but you could have a failure and then you have to deal with that process as well. Okay, yes, question.
6 never gets an OK back, and that's how it knows it won.
Yes, exactly. So 6 in this case, you will see that as part of 6 election, it queried 7. Okay, 7 is not responded to anyone. So 6 will say I am the highest ID process. It declares itself elected. Okay, that's not how things should work, but that's how it works here. All right. Yes, question.
So, does the algorithm begin with each node posting an election? Does each node send an
Okay, question is, does the algorithm begin with each node starting an election? Any process can start an election at any time. Okay. If 7 were alive, 7 would win again, even though you started an election for no good reason. You can do that, and 7 would still stay the coordinator. In this case, we say that maybe 4 is trying to contact the coordinator. It doesn't get a response, so it says, let's start an election. So it doesn't mean every node has to start an election, but some node has to kick that process off. Okay? And any process with IDs lower than it are not even involved in the election. So 4 does not have to involve 1, 2, 3, and 0. Because it already has a higher process ID than that. So either it will win or some process higher than it will win.
But if like 1 started the election, then each node will have to participate in the election.
Yes, so if process 0 kicks off the election, then you are going to have order n square overhead, okay, which is what was actually mentioned here. Because the worst case for this election is the lowest ID process initiates the election. So it will recurse, and every process will have to start an election until you get to the highest ID process. That results in order n square overhead. Okay, so that's indeed an overhead of the technique. That's the complexity of the algorithm. Okay. Yes.
Why not just make the node 4 tails node 6 node 4 already knows all the information?
Okay, so question is, why not have node 4 decide who the election is? This is a recursive process. There are other techniques that will do what you said. Okay, in this case, you basically, so the reason it's called bully algorithm is you ask higher ID processes, and higher ID processes bully lower ID processes to drop out of the election. That's why the name bully algorithm occurs. So so each higher ID process starts election and fights it out with other processes, and it may get bullied out, and then the one that's left at the end is the one that wins. Okay, but yes, I think the technique you pointed out we will see in the next election technique. Okay, yes.
And if you're referring to these as processes, even though it's this, like, because you can have multiple servers and each one be a different leader for different, like one to do a leader for time and another one to be a leader for something like that.
Okay, question is, you can have different machines or different processes that are coordinators for different tasks. So we will assume that you run a leader election within an application. Different applications can elect a time server, and some other application may elect some other kind of server, a print server, or whatever the other coordinated task may be. Those are separate elections that are run within separate applications. Okay, that's what we are going to assume. Yes.
So we assume the size 10, right? Like, so can a process come back, or is there a timeout for like this? Does 6 need to know the message replied by a certain amount of
Right.
time?
So, okay, the question is, if you have n processes, what if the processes come back and or disappear and so on, what or the timeouts and so on. So that's a good question. You can ask what happens if 7 actually eventually recovers. It was the coordinator. It comes back. Okay. So, as we said, any process can run an election. Okay. If 7 comes back and says I used to be the coordinator before the crash and now 6 is the leader, it is going to start an election. Okay, and it is going to win because there is no higher ID process, and it can then bully 6 out saying you are no longer the leader. Okay, so yeah, any process that rejoins can reinitiate an election. If a lower ID process had crashed, let us say 2 had crashed and rejoins, okay, and it runs an election, it is not going to change the outcome. The same highest ID process will win. But if the previous coordinator rejoins, it can restart the election, and in this case there is nothing to do, it will win immediately. Okay. So, that is how it will work. Any other questions here? Okay. So, that is the first of our leader election techniques. The second one is called ring based election. Okay. This basically goes back to this question saying this recursive overhead gives us order n square. Is that necessary? Once you query all the processes, you know what processes are alive, what is the highest ID process. Why go through the process of recursing and until some winner is left? Can we not figure out who is the leader based on just one query? Okay. That is what a ring based election does. In this case, we assume that processes again have IDs 0 through n, but we will also assume for leader election purposes, okay, process I can only talk to process I plus 1 and I minus 1. Okay, just for the election, not for the application. The application that these n processes are running can have arbitrary processes communicating with any other process. But as far as leader election is concerned, we will assume that you number the processes and each process can only talk to the process below it and above it. Okay. So, they form a logical ring essentially. Okay. So, here is a picture. Okay. So, you essentially have a logical ring, and for leader election you can only talk to the process below or above it. Of course, if a process has failed, you have to talk to the neighbor's neighbor, but we will assume you know how to do that. Here we see that 5 starts an election. In this case, what you do as part of the election is saying I am process 5, I am alive, and you send it to your neighbor. If your neighbor gets that message, it will add its process ID saying I am process 6, I am alive, and send it onwards. Okay. In this case 7 you have to skip over because your 7 is down. So, 6 will actually try to contact 7, will fail, and then essentially contact 0. And that message is going to trickle through the ring. Each process adds its process ID. Okay. Essentially, it will come back to the process that started the election, and that process will have a list of all processes that are still alive and their IDs. It just takes the max of those and then declares it to be the leader. That was the suggestion that was made, saying you just query all the processes, you know all the processes that are alive, you take the max, and that is the leader. Okay. That is essentially what this ring based algorithm does. What this picture specifically shows is there are actually 2 elections that started concurrently. 6 started an election, you will see that message is circulating. 2 has also started an election, that is going to circulate. Both will circulate through the ring, both will end up with the same outcome. Okay. In both cases 6 will win. Okay. This shows concurrent elections in progress, then that is okay. You can have as many elections as you want. Yes, question?
How much better is this than the previous one would depend on what the network is like?
Okay, question is how much better will this do as compared to the previous one. So, in this case you have to ask how many messages are exchanged. Okay, you will see that there are 2 n minus 1 messages. Okay, 2 times n minus 1, because you have n minus 1 messages for circulating the initial who is alive request, then it comes back and then you say 6 is the leader, then that message goes around to everyone again saying 6 is the new leader. So, you have 2 circulation to the ring. So, you have order of n in this case. The previous one was order of n square. Okay, so, it is going to be more efficient than our bully algorithm in terms of message complexity. Okay. Any questions here? Okay. So, this is our ring algorithm. So, as we said, so n processes, 1 election is progress. The bully algorithm, okay, there is a best case and the worst case. The worst case is the lowest ID node started the election. It causes recursive election at every node up the chain. That triggers order n square messages. The best case is essentially the highest ID process that's still alive starts the election. It wins immediately and it just sends out messages, which in this case is n minus 2 messages to everyone else saying I won. So, there is basically, but it is still order n square because complexity goes with worst case, but depending on which of the two it is, you will have the actual number of messages will be different. Okay, in the ring you will have 2 times n minus 1 messages always. It does not matter who starts the election, the message has to propagate through the ring twice, one to query and one to announce the result. Okay, question.
So I have a question. In the polling algorithm, the node which is starting the election sends the messages to all the nodes with higher ID than itself. Right?
Yes, in the Boolean you always send an election message to everyone with a node ID higher than itself.
So what if the node with the highest ID starts the election? Who doesn't even send the message?
Okay, so question is if you are a node with the highest ID process, what happens? Okay, if you are the highest ID process that starts an election, you simply declare the result because there is no one else to contact. Okay, so in this case, if 6 starts an election, okay, it will try to contact 7. Okay, but 7 is down, so it will declare itself the election. Or if 7 actually rejoins and it wants to take over responsibility, it can start an election and it will win immediately. Okay, so that is what the best case here is, which is n minus 2 messages. Okay, so there is a crashed process, so that's why it's n minus 2, and then you are the highest ID process that started the election. You won. There is no message to exchange. So only messages that you send are the I1 messages to the remaining n minus 2 nodes, declaring yourself the new leader. Okay. Yes. Question. Okay, what kind of events can trigger election algorithm? So you could have any event that indicates to a process that the current coordinator is not responding, current coordinator has failed, it's slow. You can use any of these processes. Of course, there are systems where the current leader can say, I resign, I am done being the coordinator, elect someone else. Okay. In these cases, you are simply using process ID to choose. So if the highest ID process resigns, it may win again. But typically what you will do is use some other metric like the load or something else to figure out the real leader. Okay. In the ring based, that's trivial to change the metric. Rather than asking the process ID, you can send a query saying append your load. So you can say I am process 2, my load is 20%. I am process 3, my load is 60%. Then you can simply choose the least loaded machine, for example. Okay. The Boolean algorithm will be a little more complicated to do it that way, but ring is easily extended to metrics. Yes.
How does one decide if a process is not, for that example, 7 is not inside, right? Like, how does one decide like that when it has not gotten a response back for like a certain amount of time, or is there something?
Okay, question is how do you know 7 is not responding? So there are 2 answers to that question. If it has actually crashed, okay, when you try to set up a socket connection to a machine that's down, TCP will fail and give you an error. Okay, that's the easy case where you know that the machine is actually offline because you can't even open a connection to it. Okay, now the harder case is where you can actually connect to it, but it's not responding to you. Okay. And then you can say, how do I know when to stop? Or is there a timeout? How long should that timeout be, and so on. That's actually a classical problem in distributed system where distinguishing between a slow process and a failed process is a non-trivial task. Okay. Because I can make the slow process infinitely slow and will look like a crashed process, but it's not crashed, it's just running slow. So you can never actually tell whether a process has truly crashed or it's running very, very slow, because it's not responding. So you using timeout like schemes can actually go the wrong way if you just use the timeout. Say it's slow enough that it takes 5 seconds, but you set the timeout to be 4 seconds, and you say it's crashed or something like that. So that's a non-trivial problem to address. Okay? But you have to make some practical choices. If it is crashed, it's an easy task. If it's running slow because it's heavily loaded or something like that, that makes it harder. Okay? So, but it's not a trivial answer to that question. What is the assumption? So the conceptual algorithm doesn't make any assumption. You just say it failed or it is not responding, but when you implement it in practice, you have to make that decision. How do I, so you can say if I connect to it, it's refusing to connect and it's clearly failed. But if you send it a request and it doesn't, you send it an election message, nothing comes back for a while. When do you say it is not responding? 5 seconds, 5 minutes, there is no good answer. You have to pick and then just assume if 7 decides to run a new election and it will win again. At that point you have to drop out. So those are all good practical things you have to keep in mind when you implement the code. Conceptually there is no limit in terms of time limit or anything like that. Yes.
Is it more common for these leader not elected leader when the leader is heavily loaded? Are those more common questions?
Right. So question is it common to elect a new leader and the leader becomes heavily loaded? So typically systems that will try to spread the load of the coordinator across machines will do something like that. So if you go back to the Skype example where we had super peers, right? So super peers were elected by the cluster, right? So a bunch of Skype nodes say you are the super peer, you are going to take care of managing our cluster. How do you decide who the super peer should be? Based on the load on that machine, the connectivity of the machine and so on. And then over time you can either super peers can resign, or if you see the load has gone up, you can actually elect a new super peer. So system has to have intelligence. Failure is not the only reason to elect a new leader, okay? Because you may have other reasons to have a new leader. And modern systems will be smart enough to do that kind of stuff. Here we are only electing a leader because it failed, but that's not the only reason. Any other questions? Okay, so we are going to now look at, so here is pictorially, here's yet another scenario where you will see that if you read the look for papers on leader election, there are hundreds and hundreds of papers. Okay. They all differ in what assumption do we make in terms of how queries are sent out, how responses come back and so on. Okay. In this case, you don't have process IDs assigned, neither is there a ring topology. So it's like a peer-to-peer network. You are simply going to broadcast a question saying who should be the leader, that and then you will see that there is capacities, which is the load on each of the links, and so that query is going to go through the system. You are going to figure out the load and then get back responses and elect a leader. It's like a ring based technique, but you are using a broadcast that trickles in a peer-to-peer fashion. Okay. That's another technique, because this is often used in a wireless network because you may not always be able to have a nice ring topology and so on. Okay, because wireless nodes have a communication range. Okay, you may not be able to communicate with a certain node because out of range and so on. So you have other techniques to essentially do this. I won't go into this technique. I just wanted to show you that there are several others. So this is, as you can see, the query is propagated and then the responses are coming back in the reverse arrow, and then you pick who the new leader should be. Okay? Similar to the ring where the query was trickling in a ring fashion. Here it's going out in a tree-like fashion. Okay. And then we talked about super peer just now. Okay. In case of real election algorithms, you are not going to use process IDs. That was just a toy example. You are going to use real metrics like low latency access. You have good network connectivity. Are you evenly distributed? So this is Skype super peer example. Okay, so are you evenly distributed in your overlay network? Are all the peers in your cluster near to you? Okay. There are some peers that are further, the latency to some of the peers may be higher. What is your load? Are you actually, depending on how many nodes you serve, you may actually split the cluster up and make them 2 clusters and have 2 super peers and so on. Because that's a P2P network, the network topology evolves over time. So who is part of the cluster, or that you split a cluster or merge 2 smaller clusters into bigger clusters, and then the 2 super peers, one of them has to be asked to become a normal peer, the other one stays a super peer and so on. So there are a lot more complexity in how you do this in larger distributed systems, especially peer-to-peer distributed systems, where there are a lot more dynamics when nodes come and go. So what happens might actually change over time. Any questions on this? That's not a description of Skype's super peer algorithm. It's simply saying what are some considerations that you might have to take into account when you do leader election in a real application. Okay, so I'm going to now describe, so I'll skip this actually, switch gears. Okay, so that was a very quick description of leader election. Okay, so you have bully algorithm, you have ring algorithm, and then hundreds of variants. Okay, the basic idea is you got to query all the nodes, find the metric that you care about, and pick the best node for that metric. Okay, and then you want to ensure that whenever you run an election that somebody wins, but you don't declare 2 winners or anything like that. It's going to result in an error. Okay, with those properties, you can implement this leader election technique. Okay. So now we will switch gears and talk about a different problem, which is how do you implement locking or distributed synchronization. Okay. All of you know what a lock does. Okay. If you write multi-threaded code, okay, whenever you try to access any shared data or you have a critical section, you have to have a lock that you acquire before the critical section or before accessing data, and you release the lock when you leave the critical section or you are done accessing data. Now, if in a distributed system, you have more than one process run on more than one machine. Okay, so you don't have one process. So the question is how do you implement this notion of a lock so that all processes agree on the lock state. Okay. The notion of a lock itself has to be distributed in this case. Okay. So how do you go about doing that? So we'll look at examples of how to do this. I'll start with a simple centralized locking approach. It's a distributed system, but we will elect a lock coordinator. We'll use leader election and say you are the master that's responsible for figuring out how locking should work. Okay. And then there's a picture here which is going to show us how the locking works. So 4 processes. Okay, 3 has been chosen to be the lock coordinator. So in this case, when any process needs to grab a lock, it sends a lock request to process 3. Okay. And then process 3 is going to take all incoming lock requests. If the lock is free, you tell the process that you have the lock. If the lock is in use, you are going to queue up that. So there's a queue here. You will see that in this case 1 has requested the lock. Initially the lock is free, 3 sends it an OK. So now 1 is holding the lock. Okay. When that is still the case, 2 sends a request for a lock. Because the lock is in use, you queue up 2's request. Okay. Eventually 1 is going to release that lock by sending a message to the coordinator. At that point, it will look at the lock queue to see are there outstanding lock requests. If so, you are going to take the request at the head of the queue and tell it saying you have the lock. Okay. So you will have to essentially generalize what you do in a centralized single one process multiple thread scenario to a distributed system. Simplest case is centralized coordinator. Okay. Now this is easier said than done, because you will ask what happens if the process crashes. Okay. In a multi-threaded application, this is not a problem. If a thread holding the lock crashes, most likely it will take down the entire process with it. So you won't have other processes sitting there saying what happened to the lock. Okay. Because if you have one process causes some sort of a segmentation fault, so all the entire process goes down. In this case, that's not the case. Okay. You can ask what happens if the coordinator fails. What happens if the process that's holding the lock fails? Like one got the lock, one failed. Okay, it's gone. It's not going to release the lock. The entire system is going to deadlock because you cannot give the lock to any other process. Okay. Because typically you don't have timeout with locks and you have the lock for 2 minutes. That's not a lock abstraction. You can change the lock semantics to say locks have expiration times. But the default definition of a lock does not come with an expiration time. You can acquire the lock, hold it for as long as you want, and then you release the lock. So we have only 2 methods, lock acquire and lock release. And it's assumed that you can hold it for as long as you want. Okay. In this case, if the process actually crashes, you don't know whether the process has gone down or it's still computing and holding the lock for a long time. So you will just keep all the other processes waiting. Okay. That makes it complicated. If the coordinator fails, it's even worse. Okay. You can elect a new coordinator. That's not a problem. You can run leader election and do it. But then you don't know what state the lock is in, unless you save the state of a lock somewhere on a disk that you can actually go and figure out what the state is. So if a lock is an in-memory data structure and you don't know, this queue will disappear with that process. Okay, the lock state will disappear with the process. You will have a new lock coordinator, but it doesn't know who is holding the lock if the lock is free. So there are all these thorny problems you have to deal with when you have distributed locks. Okay, this looks simple, but dealing with failures makes it actually complicated. Okay, is that clear? Now I won't talk about how to deal with failures here. When we come to fault tolerance, we'll see general techniques to deal with failures. Okay, so we won't go into how do you make the lock fault tolerant or anything like that. We'll look at basic concepts of how locks work without considering failures. Okay. But the failures is where this becomes complicated, much more so than centralized locks. Okay. So, this is a lock coordinator based algorithm. Okay. So, what are its properties? Okay. It's a centralized lock, okay, using blocking calls. It is fair. Okay. Basically, lock requests are going to be granted in the order in which they come in. Okay. If there are multiple requests, they will all be queued. Okay. In this case, they will all be queued. You will get a turn in the order in which you made the request. Okay. No one is getting priority or anything like that. So, it's a fair request. It is simple because there are only 3 messages. Okay. You make a request message, eventually you get a grant message telling you have the lock, and eventually you send a I release message saying I release the lock. So, there are only 3 messages to implement the entire protocol. Okay. Shortcomings are single points of failure. So, they have to do with failures. How do you detect a dead coordinator? Okay. You cannot distinguish between lock in use from a dead coordinator, and then how do you deal with a process that is holding the lock that goes down. Okay. So, and then the last thing of course is, if you have a very large distributed system, okay, that lock coordinator is going to become the bottleneck. There are lots of locks, each of them has a queue. This lock coordinator is managing lots of locks, lots of requests coming in. So, it may itself become a performance bottleneck, as in any centralized approach. It won't scale. Okay. So, that is the first algorithm. So, we can decentralize it. Say, why have a centralized coordinator? Let us actually make the process of implementing a distributed lock decentralized. Okay. So, now what we are going to use is use the concept of voting. Okay. So, here what we are going to do is, to acquire a lock you need a majority vote. Okay. So, essentially you need so you ask for a lock, every process gets a request. So, essentially every process acts as a coordinator in this case. So, you ask every process saying I need the lock, what should I do? Okay, processes are going to, if they say lock is not in use, all of them are going to say yes, go ahead, and then you need to at least get a strict majority, because some processes would have failed. The coordinator could be a process that has failed. So, you can't assume that every process will reply. Okay. So, you will assume that if a majority tell you to go ahead, you should essentially go ahead and grab the lock. Okay. So, you are simply going to use a majority vote, which is going to tell you what to do, okay, whether to wait or not. If your lock is in use, you won't even reply to that process, but eventually when the lock is released, okay, all the processes are told that this lock has been released. They all have the outstanding request. They will pick one at the head and send it out, to send a lock a grant request to that process. Okay. So, what you have done is, in this case, is taken the centralized approach and re-implemented that at every process. Okay. So, every process participates, they run the same algorithm. That way, one process fails, the others are still running that same approach that we talked about in the centralized case. So, all you want is to have a majority of the nodes to tell you that you have the lock. So, that tells you that you are guaranteed that the lock has not been granted twice. Is that clear? So, you should ask, why do you need a strict majority to tell you to get a lock? What happens if a minority of the processes tell you have a lock? Okay. So, we said you are going to essentially use voting, and you need a strict majority, which is strictly greater than half of the nodes which are implementing the same centralized approach to tell you have the lock. Okay. You can't have a minority telling you have the lock, because the others could have granted the lock to some other node. Okay. If your network gets partitioned into 2, okay, if there are 10 nodes, 6 nodes are in one group, there is a network breaks, and the 4 nodes are in another group. Okay. Those 4 nodes can't unilaterally decide to give the lock to some node in their cluster, because that will mean that the lock has been granted twice. Okay, this partition is granted to one and the other partition granted to the other one. You do not want that case, which is why you say strict majority. So, if you get partitioned and you only have a minority of the request nodes telling you that you can have the lock, you still do not go ahead and take the lock, because you wait for others to respond to you as well. Okay, that ensures correctness, or what is called a safety property. Okay, you do not want the lock to be granted twice at the same time. Okay. So, there is some probability analysis which I am going to skip here. We will come back to all of that during fault tolerance discussion, but I am going to describe yet another approach which is based on this notion of Lamport's clocks. Okay. So, this is called a Rickert and Agarwal algorithm. Okay. Here we are going to use Lamport's clock and total ordering of events and timestamps, logical timestamps to figure out who should get the lock. Okay. The approach was as follows. Okay. So, we will assume that to enter your critical section, which means to grant to get a lock, you are going to increment your Lamport's clock. Okay. So, you implement your local clock 1, okay, and you send a request saying I am process K, here is my logical clock value to all other processes. Okay. They are Lamport's clocks. Okay. And then you have to wait until you have received a reply message from every other process. The reply tells it to go ahead. So, you ask every process saying I am going to request the lock, every other process in the system, not a majority, every other process in the system have to tell it to go ahead. At that point you grab the lock. Okay. And then if some process has received a request message from some other process, here is what is going to happen. If you do not need the lock yourself, you immediately say go ahead, I do not care, go ahead, take the lock. Okay. So, if there is no contention, you send a reply. If you are already holding the lock, okay, you are going to essentially queue the request and not reply, saying I hold the lock, okay, I cannot tell you to go ahead obviously. Okay. So, I will wait. Okay. Now, if you are also contending for the lock, which means this case is not true, which means there is no contention. This case is no longer true, which means you do not have the lock yourself. The third case is I have also requested the lock. Okay. So, I am now going to compete, process I and process J are going to compete for the lock. Okay. In this case, you are going to essentially grant the lock in timestamp order, in logical timestamp order, because we assume you are doing total ordering. So, you say who asked for the lock first? Let us use logical timestamps to figure out which order it was asked, and we will grant it in that order. So, if I and J are competing, you say if I's request has a lower timestamp, I will let I win. If my request has a lower timestamp, I am going to win. Okay. So, depending on which of the two cases is true, you will either send a reply or you will queue the request. Okay. So, it is using simple notion of logical clocks to essentially get a time ordering, okay, or time ordering, event ordering, and then basically based on that event ordering decide in what order to grant the lock. Okay. So, it is a use of the basic Lamport's clock algorithm to implement a distributed lock. Is that clear? Yes. Question. Is it a distributed queue? It is like a distributed queue. Every process maintains a queue of requests. Every process uses logical timestamps to decide in what order the requests for locks have come in, and requests for locks are granted in the timestamp order. That is what is happening in this case. Yes.
Does the process block when it's, so if I request, if my request is queued, then do I block?
Okay. Question is, if your request is queued, do you block? Okay. All locks are blocking in nature. If you make a request, you block until you get a reply. Okay. However, having said that, your application could be multi-threaded, because while you may be blocked for a request, you have to have at least one thread that is processing the locking protocol itself. Okay. So, you might have to have at least two threads, one to do the actual application code, the second thread is simply implementing the lock protocol, because every process has to participate in this, maintain logical clocks and participate in the locking protocol. Okay. That thread will not block, but the actual thread that made the request will block. Okay. Any other questions? Yes.
So, for this to work, should someone send a message to every other system inside the network, or is it like can it send it to, how is the ordering?
Okay. The question is, for this lock protocol to be implemented, do you have to send a request to every process in the system? So, we will assume that distributed system has n processes. Okay. That is one application. It is not the machines, they are just n processes are part of some distributed application. If those n processes want to implement a distributed lock, one or more distributed lock, they have to participate in this protocol. Okay. Every lock request or every request and every reply messages are multicast to all other processes, because they are all participating. So, all of these n processes are multicasting to one another for the locking protocol. Okay. Other processes, other machines do not participate. Okay, only the ones that are part of the applications will participate in the locking protocol. Any other questions here? Okay, so very quickly, that's just a picture that shows how it works, but very quickly the properties of this technique are interesting. It is fully decentralized because there is no coordinator. Every process simply uses logical timestamp to reason about what can happen or what should happen. Okay, that is the good part. The bad part of this approach is that now you have endpoints of failure, okay, because you have to wait for a reply message from all other processes before you grab the lock. If any process in the system crashes and fails to get back to you, you will think that that process is for the lock and you should wait. So, you will not proceed. Okay. That creates endpoints of failure. Okay. In our centralized coordinator approach, there was one point of failure. With the coordinator crash, you couldn't figure out what to do, or if one client process crashed, you could not figure out what to do. But unrelated process crashing did not impact the locking itself. It could impact the application, but not the locking. In this case, okay, you have a fully decentralized approach, but failure of any process actually holds up the entire locking protocol. Okay. So, this is a rare case where a decentralized algorithm actually has worse failure property than a centralized algorithm. Normally, when you make things distributed, you expect failure properties to get better than a centralized approach. Okay. This is a rare counter example where actually the failure properties are worse. Okay. Not typically, that is not the case, okay, but in this case that is actually true, and that is because all processes are involved in all decisions for locking. Okay. So, any process that fails actually holds everything up. So, that is the problem. Okay. Any questions here? So, we talked about 3 different locking protocols. Okay. We are going to talk about one more. Okay. We talked about the centralized approach. We talked about implementing the centralized approach on every process, but have them vote, do a strict majority vote. Okay. We talked about a logical timestamp based approach, where every process also participates and everybody has to tell you what to do. Okay. And then the fourth approach is actually going to be a token ring based locking protocol. Okay. So, here, as the name token ring suggests, okay, we will assume again processes are ordered 1 through n or 0 through n, and they form a logical ring. The actual topology is not a ring, but they are actually form a logical ring, which essentially means for locking purposes, not for other purposes. Process I will only talk to process I minus 1 and I plus 1, your 2 neighbors. Okay. So, the locking protocol is very straightforward. You will have a special token message that is circulating in the ring. Okay. To get, essentially, you need to hold the token to acquire the lock. If you hold the token, it hold the lock at this point. Okay. If you want to acquire the lock, you just simply wait and wait for the token to come to you. Okay. The token is going to keep circulating through the logical ring. Okay. Let us say the token starts at 0. Process 0 says, do I need the lock because I hold the token? If the answer is yes, you keep the token with you and do whatever you need to do in your critical section. Once you are done, you send the token to 1. Okay. If 1 needs the lock, it will hold it, otherwise it will just pass it on. Okay. So, the token will keep circulating through the ring. Okay. Eventually, at some point, if I needs it, it will get to it. Okay. At that point, you get to enter the critical section. There is no requesting the lock at all. You simply wait for the token to come. The token keeps circulating. Okay. Whenever you have the token, you essentially can enter the critical section, do whatever you need to do, and to release it, you send it to your next neighbor. Okay. And that is it. That is all the algorithm will do. Okay. So, this is essentially a token ring locking algorithm. Okay. Now, this protocol, it is very straightforward. This was designed in the days when token ring was also a LAN topology. Okay. In the early days of local area networks, there were 2 topologies: Ethernet, which was a shared access medium, okay, and there was token ring. Okay. Now, in both cases, you had to ensure that only one machine can transmit on the LAN at any given time, otherwise your packet collisions. If 2 machines on the LAN try to send packets at the same time, because it is a broadcast based medium, okay, you will essentially have packet collision. Okay. In Ethernet, you use a randomized back off protocol. If there is a collision is detected, you back off for random periods of time. So, the 2 nodes that both transmitted at the same time basically back off at different times and start transmitting independently of one another. So, you use randomized technique to avoid once you detect collision to not have it in the future. In token ring, you use the notion of a token to figure out who gets to transmit. Every PC on your LAN has to, before it can transmit any message to any other machine through whatever TCP, IP or whatever protocol you want, you have to wait for the token, because token is a lock on the LAN in this case. So, you hold a lock on the LAN, no one else holds a token. So, it is guaranteed that if you transmit any packet to anyone else, there will not be any collision. Okay. So, that was the context in which this locking protocol was developed. The lock you are going to actually grab was actually a lock on the local area networks to transmit. Okay. But that, of course, token ring LANs no longer exist, okay, Ethernet 1, but the locking protocol is still robust. You do not really need to use it just to decide when to transmit. You can use it for any locking purpose. Okay. So, that protocol is still a useful one, and you can essentially use it to implement any locking scheme. Okay. But just as in token ring, okay, detecting loss of tokens is an important problem, okay, because network can actually cause a packet to get lost or corrupted. If the token disappears, then what should you do? Because now you will not have the lock anymore, because if A is transmitting, if 5 is transmitting to 6 and there is noise on the that corrupts the token packet arrive at 7. Okay, now what should you do? Because the token is lost. Okay. Regenerating the token is not a non-trivial problem. Okay. In the token ring protocol, okay, that problem was somewhat easier because you could not hold the token for arbitrary periods of time, okay, because you are essentially doing network transmissions. Everyone needs a turn. There is a maximum duration for which you could hold the token. If I send the token, wait for, but in an arbitrary locking protocol, you can hold the token for as long as you want. Okay. So, if the token has not come for a while, you can't say I will time out and regenerate the token or anything like that. In the old token ring LAN protocol, you could do that. If the token could be held for max of 1 milliseconds, and there are in this case 8 nodes, every 8 milliseconds you should see the token. If 10 milliseconds are gone by, token has not arrived, you know that token is lost. Okay, there is a easy timeout property there. Okay, if you are implementing arbitrary code, you can't say you can only hold the lock for a millisecond. You can hold it for as long as you want. That is a critical section. That depends on your code. So, you can't write some timeout techniques to figure out when to detect the loss of a token, how to regenerate it, and so on. It's the same as coordinator failed. Okay, now I don't know if I'm not getting a lock, is there a problem, is there a failure, or someone is holding the lock for a long time. It's the same problem here. Okay, so, the failure recovery is much harder in all sorts of distributed locking protocols. Okay, that's the thorny part here. Okay. Again, we won't go into how to deal with it now. We'll come back to it when we talk about fault tolerance. Okay. So, we ran out of time. I'm going to stop here today. We will not have a class on Friday. I announced that. So, next class is a week from today. Okay. No class on Monday either.